Vale. Voy a hacer un breve resumen de lo que vimos ayer, para que sepamos todos dónde estamos y después ya cuando entre en materia veremos ahí. Acordaos que habíamos introducido todo el lenguaje algebraico asociado a las variedades diferenciables y como los espacios de funciones entran anillos y como los campos vectoriales y los campos tensoriales en general son módulos sobre ese anillo de funciones y como además las operaciones naturales entre esos tensores, pues como el producto tensorial o entre las formas diferenciales el producto de cuña, eran además ejemplos de álgebra, ejemplos de infinito álgebra. Acordaos que una álgebra muy importante era el álgebra del Lie de los campos vectoriales, que es un poco más sutil que eso, porque como Martín mencionó, como Gabriel mencionó, la multiplicación de funciones por campos vectoriales corresponde a esa idea de reparametrizar, esa idea de velocidades. Y digamos que el corchete de Lie que encontramos en el infinito módulo de campos vectoriales no es un ejemplo de infinito álgebra, es un ejemplo de álgebra, pero no de infinito álgebra. Y es precisamente esa interacción entre la estructura de R álgebra, que también la podéis entender como álgebra respecto a funciones constantes, es lo que acabo de hacer. Y esa estructura de R álgebra respecto a la estructura de infinito módulo, que está presente en todos los campos vectoriales, en todos los campos tensoriales, es un poco lo que comentamos sobre las derivadas covariantes, sobre la introducción de conexión y sobre toda una rama de estudio de la geometría diferencial que consiste en estudiar esa interacción. Entonces hoy es cuando vamos a hablar de física por primera vez. Vamos a pasar a la parte de física, de geometría y física. Pero antes quiero dar un breve resumen, no voy a darlo con mucho detalle porque si no seguramente me llevaría la clase entera. Un poco explicar con algo más de detalle el álgebra exterior, ¿vale? Se conoce como el álgebra exterior y que ayer simplemente mencionamos como un ejemplo de infinito álgebra, pero vais a ver que igual que en los campos vectoriales tenemos un corchete de Lie que tiene una interacción con la estructura de infinito módulo interesante, digamos, me gusta llamarlo una interacción tipo Leibniz porque cada vez que aparece una combinación de dos elementos de alguna manera multiplicados, la forma en la que interaccionan las estructuras algebraicas es tal que se expande con la regla del producto, de derivación de toda la vida. Pues vamos a ver que esto se manifiesta también en las formas diferenciales. Alright, so let's do it in English from now on. So remember that we have in any manifolds, we identify the ring of functions. And from here, remember the theorem that related the derivations of this ring, which is something that is always algebraically defined as this set of endomorphisms that expand the products as the Leibniz rule. And remember that this was identified with the set or the space of the vector fields. And remember that this we saw as our algebra with respect to a Lie bracket. So it is a C-infinity module in the sense that we have a notion of function times a vector field, but it's not a C-infinity algebra because if you plug a function in one of the arguments multiplying one of the vector fields, you don't get just the linear term. You just don't get the function outside the bracket. You get some Leibniz-like formula. So now what we're going to pay attention to is this thing. And I'm going to remind you of the basic definition of this object. Remember that we identified, notationally at least, this sort of trivial notation here that we call omega naught, omega 0, just the ring of functions. It was simply a name in anticipation of this bigger guy. And we also identified the one forms, we even used this name, one form, several times, to refer to the sections of the cotangent manifold. Okay, so these were the tensor fields that assigned covectors smoothly over your manifold. Okay, so now what we're going to do is, and remember that we identified k-forms is perhaps something we didn't do explicitly for the case of affine spaces or of manifolds, but we certainly did it for the case of vector spaces. And remember that we defined the set of all antisymmetric tensors of a vector space. So this is the same idea. So this is the sections of the antisymmetric tensors. Okay. So I wanted to remember simply the spaces we defined in lecture, I think 2, where we simply assume antisymmetry of all the arguments of our multilinear forms. In this case, these are going to be tensor fields over our manifold that take k vector fields as arguments and spit out functions over the manifold, and do so in a fully antisymmetric way. So if you exchange any 2 arguments, you'll get a minus sign. So what we're going to do is put them together in one single big algebra, one single big. So remember that the standard example of an associative algebra that we found was that of the tensor algebra of a manifold, which meant you took all the tensor spaces of all the ranks, put them together with a direct sum, and then you realize that the tensor product allowed you to multiply and get higher and higher ranks, or orders. So we're going to do essentially the same. So the definition here is the infinite sum of these guys. But remember that we discussed how when we get to the rank equal the dimension of our space, the number of arguments somehow saturates or non-vanishing values of the form in a set of arguments just saturates, and we go to n plus 1 number of arguments. There's no way the value of the form doesn't vanish. So I can simply write here n, where dimension of my manifold is just n. Okay? So what does this mean? This is simply, it's not a big bag, like I referred in the past, una bolsa donde ponemos las cosas. It's actually a structured, it's more like a shelf. I'm tidying things up. I'm not just throwing them into a bag without any further structure. I'm tidying them up in a sort of shelf. So that's why I'm writing. This works with me. I'm going to the third part of the blackboard. Okay. So this is what this object is. Okay. So remember that this totally antisymmetric forms, one of the exercises was that you show that they are closed under, yes? So remember that the first, well, there's of course the module structure, this infinity module structure of each of the summands of this direct sum. And therefore, there's the direct sum of the module structure in a trivial way. So if I have a function that I want to multiply by an element that is some linear combination of these forms, you just multiply each of the components, a bit like what you do with Rn as a vector space. Okay? So we have that. Have this thing being a infinity of m module. Remember, this is the notation that we used yesterday. But there's more. Remember that the wedge product was graded antisymmetric, meaning that perhaps depending on the grade of your form, you might get a plus or minus sign, but in some sense, antisymmetric associative product. And today we're going to see that there's another natural structure induced in this algebra that we call a differential. So this becomes a differential graded. We haven't really talked about grading. The grading just refers to the fact that we have elements ordered up, so we have some way of tidying them up. Differential graded algebra. So what is this thing? So the notation already suggests that I'm somehow referring to the differential of the function. I gave you the same name and I gave you the same symbol, so chances are I'm going to do something like that. So remember, what was the differential of a function? The differential of a function, using the notation here introduced, took functions, which we identified by convention with zero forms, and gave me covectors at each point. Remember, a couple of pages back in your notes, you should have that the differential of a function would take, when evaluated at every point, will take tangent vectors at that point and will give you real numbers. So that's why we identify them as elements of the cotangent space at every point in the manifold. And so when thought of as a smooth assignment in your manifold, just smearing some values along your manifold, we get a field of covectors for every point of your manifold. So a function that is a smooth assignment of real numbers to your manifold gets a differential, which is a field of covectors, right? Of course, it's calculating this notion of you give me a direction, and I'll give you the directional derivative in that direction. So the instantaneous rate of change of this function in this particular direction. Okay. So I didn't say it as an exercise, but I could say it now. Show that, well, I think we did discuss about linearity, maybe not directly, but show that this is the case. Okay, that's very easy. Just look at the definition. It's a very easy proof. And equally easy, perhaps a little bit more clever, to do work with the definition of derivative and so on, is to show that when I take the product, and what I'm doing here is simply asking the natural algebraic question. My zero forms are functions, and my functions have two algebraic operations, addition and multiplication. So all I'm asking is, how does this operation interact with this basic structure? Right? And what I'm writing down is essentially the only thing I can write down. So for the differential, you can show by simply computing that this is the result of computing the differential. You might be wondering, why have you changed the order here? Does it mean anything? Well, it does in this context, because for the product of functions, we have symmetry. But here, this is no longer a product of similar objects. They don't belong in the same space. This is a function, and this is a covector. So this is a one form. Sorry, this is a one form, and this is a zero form. And what I have is the module structure. The module structure for any tensor algebra, or any tensor bundle, gives me the rule how to multiply these things. So that's why I have to write f times this, g times that, in that order, because I haven't defined what it means to do this. I could say, well, that means just doing that, and you can completely forget about this subtlety. But technically speaking, I don't want to load my notation any further. Okay, so that's an exercise. And so we've seen that this operation interacts with, well, first of all, it's linear, so I'm going to regard this as a linear map. It's an operation here, like this. And it acts as a derivation. Remember yesterday when we defined derivations of rings and modules? And this is precisely what this is doing. This is giving me a Leibniz rule, or Leibniz formula, for the interaction of the operation with the multiplication of functions. Okay, so remember that by convention, the wedge product of forms, which we simply define very generally as the antisymmetrization of the tensor product, you must remember, or perhaps do as an exercise if you never saw it before, that when you take functions as zero forms in this sense, the wedge is by convention defined to be simply the ring multiplication. This is simply the pointwise multiplication of functions. And in general, the multiplication, the wedge of a function with any form, any arbitrary form, is defined to be the module multiplication, right? This idea that we can multiply a function times a tensor. And intuitively, remember what we are doing is nothing mysterious. We're simply saying at every point of your manifold you have a tensor. That's where, sorry, at every tangent space of your manifold you have a tensor. That's a tensor field. And if I give you a function which gives you a distribution of values around your manifold, we'll just evaluate everywhere and just use the linear structure of each of the tangent spaces to multiply a scalar times a tensor. And that's what this symbol means, right, which has been used here as well. Okay? So knowing these conventions, well, this is not a convention, this is a convention. This ends up being, when you define it as antisymmetrization of the tensor product, then we can rewrite this formula as follows. Sorry. Just essentially going to write the same, but I'm going to reorder a little bit. Because obviously this is antisymmetric, so this is greatly antisymmetric, so I have to make sense of what it means to multiply in the two directions. So I basically, this is now symmetric, so it's really by convention this operated, so that the expression looks a lot more familiar. We have this, right? So the differential of a function becomes a derivation with respect to the wedge product. And this is a triviality at the level of functions, but I don't want to say it as an exercise because I haven't really given you the machinery to prove it, but it can be shown that this operation is extended to all ranks by extending as a derivation. What does it mean to extend as a derivation? Well, you know how to act on zero forms by simply taking the differential. And then what we do is we say, well, we're going to, given any two forms, we're going to establish that this interacts in this way. So yes, I have to give you the definition of this one first, actually. And okay, so to close out the story, because I don't want to spend more time with this, I advertised the structure present in the exterior algebra as the dual manifestation of my Lie algebra of vector fields. So I need to make this claim more precise. And this formula here, let's argue somehow backwards here. If I give you a rule to, remember, of course, remember that the wedge product was just the antisymmetrization of the tensor product. So if I give you two zero forms, it gives me another zero form. If I give you a zero form and a one form, it gives you another one form. So only with one forms and zero forms in this way we can produce all the orders. But if I give you one forms, then you can wedge them together and you can get all the orders by combining them, because I wedge a one form and a one form and I get a two form. I wedge a two form and a one form and I get a three form, and so on. Right? So if I knew what this operation is, so if I knew, let me write it here, how to go from one form to two forms, then by imposing this formula, we'll be able to calculate exterior derivatives of all the ranks. Okay. So how do we do this? Well, let me call this alpha. Let me call this d alpha. Okay, let me call this beta. So beta is a 2 form. So what I need to do is feed it 2 arguments and just tell you what this is. So first of all, it has to be antisymmetric, otherwise it wouldn't be a 2 form. And we have to somehow only use the information that we are provided one alpha. It's one single 1 form. Okay, so the key idea here, and this is somehow the moral of the story, I'm not really going to do anything with the exterior algebra. Maybe Gabriel will say something about it, but myself, I'm not really going to work with the exterior algebra. But the moral of the story is that by passing to this algebraic interpretation or this algebraic point of view of differential geometry, what was a pointwise linear algebra fact now becomes a module global fact. So what do I mean by that? Remember that we identified pointwise, by a pointwise argument, we identified the tangent, the cotangent spaces with the tangent spaces. And this was done pointwise, so I just write isomorphism as vector bundles, right? So what this means is that, or what this implies, is that when we consider the sections of these bundles, remember the sections were something like this, the 1 forms, and on this side, we have the vector fields. So now, duality here is C infinity duality. Okay? So when you have a module, remember I said this is the same as a vector space, but just changing your field. Remember, field in English is cuerpo. Your field for a ring. So the idea of a dual, you have a module over a ring. The dual module with respect to that ring is simply defined as the set of linear maps that go from A to R. Right? There's no mystery here. It's the same notion. But obviously it's algebraically a little bit more, geometrically, sorry, a little bit more sophisticated, because obviously we're taking all our objects are infinite dimensional in the real sense, and things, if you want to deal with them very explicitly, you might get into technical trouble, but algebraically things are quite clear. So this pointwise fact implies this pointwise fact. So what this means is that 1 forms eat vectors for breakfast. Right? That's what it means. And that K forms in general like to eat K vectors for breakfast. Right? So that gives me a very interesting sort of triangle of interactions, because if let me just put it here, it means that I have 1 forms here, I have vector fields here, and there's this pairing, which is the fact that this is the C-infinity dual, that sends pairs into functions, right? So it means that if I have a 1 form and I have a vector field, I have a natural way to associate a function to that pair. And you can always regard a 1 form locally as a differential of some function. So this is really the algebraic or the module theoretic manifestation of directional derivatives in some sense. Okay. So bearing this in mind, and by the way, the notation we're going to use is what you expect. I have alpha, I have x, and this, which is a function here, is simply alpha applied on x. I'm just using the common dual space notation in this sense. Okay. So that said, let's see what we can write now. So I have 3 bits of information. I need to fill in 2 arguments, so I have 2 vector fields, and I have an alpha, which is my data, my 1 form that I want to calculate the exterior differential of. So what can I do? So there are 2 things that I can do, essentially. So if I have vector fields, I have 1 operation that I can do with them, which is the D bracket. And if I have a one form and vector fields, I can plug them together with this pairing I just mentioned because they're dual to each other. So let me write them down. So I can add alpha on x. Okay. I can add alpha on y. Right? And I can operate. Remember that this needs to be a function in the end. That's where we're going. We need a function in the end. That's why I'm writing only things that are functions. And I can write alpha on another vector field that is x and y. So these are all the basic combinations of arguments that are given this way. So you could be tempted to just like write classes and try out and so on. And yes, there's a degree of trial and error in what this definition works. But remember that this needs to be antisymmetric. So the immediate guide in your definition of the differential is antisymmetry. So if I change my arguments here, this term is antisymmetric. So we're good with this term. But these two are clearly very strongly non-antisymmetric. So you could, the other more important, I would say, even than antisymmetry property is C-infinity linearity. This needs to be a tensor. So I don't think I mentioned it explicitly, but it was implicit every time I talked about it. Forms are C-infinity linear in their arguments. All the tensors we defined, that's what it meant for them to be algebra operations. They were C-infinity linear. So what that means is, perhaps, here. What it means is that these things are C-infinity vector spaces, quote unquote. They are C-infinity modules. So if I consider something like this is like a dual vector acting on a vector times a scalar. So by definition, they are linear. So this is what you get. And similarly for arbitrary number of arguments. So in particular here, if I plug f times x or f times y, I want the f to be multiplying the whole tensor, the whole expression. So we're running into trouble if we just write this, because if we multiply f here, there's no way I can get a factor out of this. But most importantly, I have a bracket here. If I put an f here, remember yesterday, I get a Leibniz-like formula, which with one of the terms being linear in f and the other term having this. And what I'm saying is if I put an x and f here, I'm going to get a term that is linear in f, that is still linear in f. This is troublesome already. Sorry, it's not f here. It's troublesome already because there's no f. I'm not going to be able to pull it out. And there's a term here that involves something that is not linear in f. So it doesn't, this is the differential of f, or the directional derivative of f. So for this to be f times beta in this way, I'm already running into trouble. But if you just look at it carefully and you see what you're lacking and what you want, you see that this is not a function, this is not a function. So functions, according to this rule, according to the fact that vector fields are derivations of functions, allow me to operate functions into functions, right? So I can just take, actually, let me change the order. I can operate a function with a vector field simply as a directional derivative. And for antisymmetry, I'll put a minus sign here. I operate this function with that. And I think, if I remember correctly, that's also a minus for the definition to work. Okay. So I could have written the definition down and just told you, okay, this works. But I want my whole expectation for this first half of the lecture is that you see that the interpretation of vector fields and one forms and functions as modules or rings allows for a very straightforward path into what's called Cartan calculus, which is what we're doing. Okay, so this is now very well defined. So the alpha is just beta with this definition. Okay, and you can check as an exercise this is antisymmetric, and you can check, most importantly, that if you use, instead of alpha, some arbitrary one form, if you use a df of some f, and you calculate d of df, what you obtain is the zero form. So you get something that always vanishes. Okay. So what we found is, at least in the first two terms, we found something that's called a complex. A complex is a vector space or a module where you have all these different components, and you have a linear map that respects the degree somehow and allows you to jump in steps. And when you compose two of them, you get 0. Okay, so somehow you can make things cannot get very complicated along the way by following D, because they die out after 2 steps. Okay. So, okay, remember, the differential of function is given simply by our basic structure of the manifold. If we take seriously the fact that functions are rings, vector fields are the derivations of this ring, and the one forms are the C-infinity duals, these ring duals of those derivations, simply using that structure, we can define what it means to take the D of some alpha, and we check that that D is in fact nilpotent, meaning it vanishes with its own lower order counterpart. And then by extension as a derivation with the wedge product, we get an exterior, a map from in all the orders. Okay. Okay, so this is what it's called, the differential graded algebra of a manifold. Sometimes for short, it's the exterior algebra of a manifold. So let me briefly just comment on a couple more. So simply, what is the Cartan calculus in a manifold? And with that, I'll finish. And let me get my phone so that I don't run over time too much. Okay. So simply as a reference, because I'm really running out of time, notice that this fact that the vector fields are the derivations of functions. So vector fields themselves send functions to functions. And that the differential sends, perhaps it's convenient to write this diagram so you to keep it in mind. It's not a very precise mathematical diagram, but okay. So derivations make the vector fields act on functions. One forms make the dual pairing make one forms act on vector fields to give functions. What else do we have? We have D, which sends functions to one forms. We have the bracket that sends vectors to vectors. And what else do we have? And we have, of course, the fact that these two things are C-infinity of m modules. So I can multiply a function times a vector field, and I can multiply a function times the one form, and I get more of those things. So this is this is not a precise mathematical diagram, but it's for you to see what things are available, right? So we can, if we give a special name to this pairing, we can sort of flip things around and say, well, alpha of x could be understood as you give me an x, and I'm waiting for you to provide an alpha to compute that value, right? So I have an operation that is waiting for an alpha, and it's defined simply as alpha acting on x in this sense. Okay, so this is what's called the interior product. So notice that we can extend this to more general forms. So for example, a two-form omega that has two arguments. So omega is naturally two arguments. This object here, in the same way that Ix that I just defined takes a one form and gives me a function for some fixed x. More generally, I can take a two form and give the form that corresponds to filling the first argument with x and leaving the second argument empty. So that is, a two form gives you a one form. So in general, you can easily see that this extends to all the orders, and I have something like this. I have this operation for all orders. And then lastly, notice that this was an exercise. X, so this action as derivations here. Remember, okay, at the end, over here, should be, this is the ring multiplication. I have a way to multiply elements together. Remember that isomorphism of derivations of the ring of functions as vector fields meant that vector fields, of course, act as derivations. So it means that there is some nice interaction of this action with this multiplication. And essentially, we can regard these operations, or this pairing operation, as a form of multiplication. If you somehow regard these two things in the same space, we're multiplying elements together, and it's like a product. So you could be wondering, what is this thing? That, by the way, appeared in the definition of the direction of the differential of one form. So what is this thing? I'm asking, what is the derivation of something that looks like a product? If you are inclined to use coordinates, or maybe you come from physics, you will see that there's functions as components of alpha, and there are functions as components of y. And we're taking derivatives, now literal derivatives, with x. So you're expecting a Leibniz rule here, because you have some pointwise product of functions. But algebraically, you can simply say, okay, if I regard alpha on y as a product, let me write the only natural Leibniz rule that I can write down. So I know a way to act with x on y. So let me act x on y, which is this bracket. But I don't have a way to necessarily act with x on a one form for it to make sense. I could use this map I here, but it wouldn't work, because it will give me something that will not be a derivation anymore, and things will break down. So I need to come up with a new thing that I call the Lie derivative of alpha. That is a new alpha, so it's a new one form. And so we see that, imposing the Leibniz rule, I can identify a notion of vector fields acting on one forms as a derivative, because we could act vector fields on one forms as this interior product simply by filling the arguments. And now we can act on one forms with vector fields as a derivative, which is extending the way they act on functions. Okay. So what we found is for omega 0, we have x acting as a directional derivative, or as a derivation in this case. For 1, we have this notion of the Lie derivative there. And what I claim here is that we can extend this to the notion of Lie derivative in all orders, and find a derivation. So what all these operations do, so this set of operations, so let me just say the exterior algebra with Dix Lx, this is what's called the Cartan calculus. Okay? So, what do I want to say? Yes, the one unifying property all these things have is that they are derivations in the okay, let me specify here. But this is the wedge algebra, the exterior algebra, and they are all derivations in this sense. So k here is the order of omega. So the way to see this is that d goes, acts on omega and then goes through omega, and then you pick up k to the power of -1, which is the number of times you have to swap arguments through omega to act on eta. So d here could be any of the above. they all satisfy the same property. And there's a list of formulas. So there's Cartan's magic formula that sometimes is taken as the definition of the Lie derivative. There is, well, when you take Lie derivatives in different orders, what you get is the Lie derivative of the Lie bracket of vector fields. The interior products just commute, which should give you the sense that they are simply correspond to filling in arguments, and so there's no sense of derivation there. There's no sense of derivative in that construction. There's a sense of derivation with respect to this associated product, but there's no sense of derivative because nothing is being differentiated. And so this is reflected here in this bracket. And then we also have this natural compatibility condition that we do have some differentiation because we have a Lie derivative there. So this becomes interior product of x and y. Okay, so now I'm basically out of time, but hopefully in the last 20 minutes, because we are running 10 minutes late as usual, let me talk about physics. Okay, any quick questions about exterior algebra? Probably you're in some sort of limbo now, floating with all this nonsense. But again, the moral of the story is that if we sort of went through the, in my opinion, not pain, but maybe someone's opinion, pain of identifying rings and modules and all these structures, and we were careful enough to notice what were the canonical operations that we could define there, then the usual operations that everyone uses in differential geometry, and when you open GR book, differential geometry book, you always find all these operations, actually arise in a very canonical way. They are there from the beginning. It was just our job to go find them and go identify and give names and give symbols to them. Okay. So let's finally talk some physics. Okay. About 20 minutes. So, okay. What I'm going to do is I'm going to summarize the formalism of Newtonian mechanics that everyone knows. We basically are born into Newtonian mechanics. And hopefully, I'll point out what the philosophy of the canonical formalism of Hamiltonian dynamics is for reinterpreting Newtonian mechanics. Okay, so quite briefly, I just need to go back to affine spaces. We're done with all the sophisticated manifolds, modules, and we're done with that. I will only mention rings perhaps tomorrow in relation to how we deal with units in physics, how we deal with dimensional analysis in physics. But we're done with the algebra, basically. Okay, so what is Newtonian mechanics? Okay, so we now have all the ingredients, all the basic mathematical ingredients to actually define Newtonian mechanics in some precise way. So the first thing we need is some universal time that I'm going to take as a parameter in some interval of the real numbers. Okay, that's related to the talk on the foundations of special relativity, where we saw how time is universal for observers in a Galilean spacetime. So this is reflected here, that we have one favorite parameter that is going to parameterize our curves, which come into play as our particles. So particles are parameterized curves xt in some affine space. I could go further. I could further say, okay, this is actually three-dimensional affine space with an Euclidean metric. I don't need to go. I don't need to be that specific at this point. Okay. What I do need to say is that this affine space is in fact a Riemannian space, or a Riemannian manifold. So I have a metric which gives me two very important notions. The notion of angle, which in some sense, allows you to quantify to what degree two vectors are not the same. Because if you're in a vector space, in a completely abstract vector space, the only thing you can really tell about two vectors is whether they are linearly independent, so parallel, either in the same direction or the opposite direction, or they are different. That's all you can say in an abstract vector space without any further structure. But when you introduce something like a metric or like an inner product that we saw a couple days ago, we can quantify to what degree vectors are different. You can say, are they orthogonal? Are they 30 degrees apart, and so on. So we have a form of, angle ruler to measure how different angles are. And we also have a literal ruler to measure how long vectors are. Because the other thing is, in a vector space, without any further choices, no choice of basis, no choice of special elements or anything, a single vector has no length. And by that, you might wonder, what do you mean it has no length? Well, there's no meaning for length of a vector, because if I give you simply a vector space V and I give you an element of this vector space, and this is the 0, where is the notion of length of this thing? There's no notion of length. The moment I specify something else, then we can start to work things out. If I give you a basis E, or one fixed element E, then you can immediately say, oh, V is this number of times E. And then, yes, there's some notion of V is this number of times the length of E. But if I don't specify anything else, there's no canonical notion of length in that vector space. Okay? And particularly, even when you want to specify basis, the length is not canonically associated, because the number you associate to V is completely different when I choose E or when I choose U here. There are two different numbers. One is positive, one is negative. There's no structure. Well, it's a bit of structure, but it's very inconvenient for the usual notion of things having an intrinsic value that is its length. You want to measure this table once and once again and once again and always get the same number if you're using the same units. So this is a bit of the intuition of how the Riemannian structure of a Newtonian fine space help us. Okay, so remember that yesterday we mentioned that whenever we have a Riemannian structure in a space, we immediately have Levi-Civita's theorem. So we have a connection that is telling us how vectors are going to act as derivations from other vectors in a canonical way. So this Riemannian structure gives you the Levi-Civita connection. And so what is the Levi-Civita connection doing? So remember that I have this expression, which is again a vector field when x and y are vector fields. So how can you interpret this? So again, this is going to be very schematic. It's going to be a sketch of what it really is in depth. But basically what we can interpret here is that x is a flow of direction. It could be, for example, part of this curve, like this. So that this curve is an integral curve of x. And then y could be some vector, some other vector that lives along the curve. So this quantity here is going to measure how this vector changes, how it's transported along the curve. And by transported, I mean parallelly transported. So if your connection is non-trivial, this transport is going to be non-trivial. So you're going to change vectors around. So the cartoon that we always refer to explain these kind of things is, think of a space where the curvature is not 0, and basically take one vector here in the north pole, say, okay, and now take this back. I'm going to go through here, I'm going to go through here, I'm going to go through here. So parallelly transporting means I'm not going to change the angle of my my tangent vector, of my vector here, sorry. Let's say that I begin in this direction. Okay? So parallel transport means that I don't change the angle of this vector with respect to this curve. So these are always straight angles. Okay? Because they are, not because they are straight, but because they are constant. There's no changing. I assume they are straight in the beginning, so they don't change. I'm going to transport them along this one, meaning the angle is always pi, in this direction. And I'm going to transport it here in this way. And I'm never changing the angle of the vector with respect to the curve, right? And then when I get here, you see there's a 90-degree angle between the initial vector and the final vector. And all I did was transport it parallelly with respect to the path. Remember, if I play the same game in the plane, if I have a vector here, and I parallel transport it, I'll get back to the same. So it's really the geometry of this space that is making the vectors do weird things. So mathematically, what's happening is that the metric that the flat space has is, well, curvature free, and therefore the connection has derivatives or covariant derivatives that parallel transport vectors in that way. Whereas, and so the difference is no longer is zero. Whereas generally the difference might be zero, like in this case, if you take the metric that lives on the sphere of the ground metric, then this derivative no longer gets you back to the same point. So we have the notion of where are the curves that parallel transport themselves. So this is the generalized notion of straight line. So you don't need a flat space to talk about straight lines, because what is the property of a straight line? So in our intuition, straight lines have two fundamental properties. One of them, for this discussion, is that if you have a tangent vector in that straight line, that tangent vector remains tangent to the line when you parallel transport it along the line. So obviously the tangent vector to a line is always tangent to the line. By definition, it's the tangent vector of the line. But if you take it at any point and you parallel transport it along the line, the vector remains tangent. This is non-trivial. So when in a space, if I take the tangent vector here and I parallel transport it, I get this here. And that is clearly not the same as the tangent vector. So clearly that property fails for a curve, for a general curve. But in flat space, if I have a straight line, the property is if I take a tangent here and I parallel transport it here, and I can compute the tangent there, it's the same. Right? So that's a fundamental property of straight lines. And if you play around a little bit with what it means geometrically to have a connection and a covariant derivative, you can check that this notion for vector fields can be done for positions. Let me know this. I'm going to get confused with my annotation. Can be applied to just vectors at every point with a parameterization of a curve. And so this quantity here is essentially measuring how much the tangent vector of a curve is being paralleled by the curve itself. It's being parallelly transported by the curve itself. So demanding that this is zero, that this vanishes, is a definition that the curve x of t is a straight line. Okay? And I'll finish with this, because otherwise we're going to go well over time. The other important notion of a straight line in our intuition is that if we fix 2 points, and with this I'm connecting with Alberto's talk, Alberto's course, is that if we fix 2 points in space, there's obviously infinitely many paths that I can take to connect those 2 points in space. But the metric, the presence of a metric, remember, gave me 2 notions. An angle, which allowed me to talk about parallel transport and all these notions of how things are parallelly transporting themselves, and the notion of straightness in some sense. But it further gave us the notion of length of vectors. So by using the fact that this is a tensor field that is smoothly taking values over my space, I can define the notion of length of a curve, as Alberto already wrote in the blackboard yesterday, I think, as simply the value of the metric, somehow the norm squared of the tangent vector of a curve. Okay. I didn't put it here, but I'm referring to x naught of t as this, as the tangent vector of the usual condition. So this is now a function in t, right? And so this is the interval where my t's are taking values. This thing, you can say, is the length of the curve xt. Perhaps use a functional notation if you want. In my curves, this is reserved for directional derivatives. So obviously, the other important property of straight lines is that they minimize, at least locally, they minimize this length, right? We know that by following a path where we just look at our feet and we just make sure that our feet are always parallel to each other, we make sure that wherever 2 points were connected are going to be linked by the minimum length path. And this is a trivial statement in our space, but in other spaces this is no longer true, right? Or at least no longer true when there's no metric and there's no notion, or the notions of length and parallel transport are different. A Riemannian structure, a metric, means, or gives us a notion of these two things being the same. And so the notion of a curve x that minimizes this quantity for any two fixed points is what we call a geodesic. And this is from the historical name of geo, earth, and then geodesia was the science of measuring the earth. So geodesic was, and this was obviously very important for sailors to travel around the world, to know what is the shortest path to get between 2 points of a sphere, because they were practically thinking of really going around almost to the other side of the sphere. For example, when traveling in the Pacific or through the Atlantic and from, say, the Netherlands to Brazil, I mean, that's a very big arc in the sphere. So you need to know what is the straightest line or the shortest path. So geodesy was really the birth of modern differential geometry. It's just a historical note. And Gauss was somehow compiling all the knowledge of this geodesy, the tradition of geodesy, and with his student Riemann, and then eventually founding differential geometry. Anyway, so the notion of geodesic is that of minimizing a curve of minimizing length. So how do I say that? So it's a curve xt, so this is minimized. And I'm going to say locally, because clearly the example of the sphere is already telling you that this notion needs to be local, in the sense that you're claiming that there will be some region of your space in which you could find a unique solution to the geodesic problem. But it doesn't mean that the solution is global, because it might be possible that you can go around the sphere and your space might be complicated, it might be more than one geodesic with the same length and all these kind of things. So, I mean, the example is in the sphere, any two antipodal points. What is the shortest path between two antipodal points in the sphere? Well, infinitely many. So it doesn't matter in which direction you go, as long as you walk in a straight line on a sphere, you will reach the other side in a minimum length. But it doesn't matter in which direction you travel. Right? So this is why I have to say only locally, because the topology of our space can really affect this notion. Okay, so this is basically this is the context in which Newtonian mechanics happens. We have position space that has a notion of straight line and geodesic. Let me say this is straight line. This is geodesic. And it's a theorem that the notion of straight line is given by the presence of a connection. And in fact, the name connection, if anyone is wondering, that name sounds totally intuitive, and I'm not saying anything intuitive in some map between the algebras or whatnot. The name connection is precisely related to this idea, how you connect points in the manifold, how you transport between those points. So the presence of a connection gives us the notion of a straight line. The presence of a notion of length, so some functional on your, possibly definite functional in some sense on your curves, will give us a notion of geodesic. But through the Levi-Civita theorem, a Riemannian structure on our space gives us both. And they don't necessarily need to match by coming from the same object, but in fact they do. The notion of local geodesic and the notion of local straight line is in fact equivalent. And this is one of the most standard exercises in a more advanced course on Riemannian geometry, is to show that geodesics and the straight lines in this sense are the same. Okay. So that means that there is a very favorite family of lines, a very distinct family of lines in a Riemannian manifold, and those are the geodesics. I'm not going to call them straight lines anymore because that's a bit unconventional. But anyway, the geodesics are the natural free flow of particles in a Riemannian manifold. And so Newtonian mechanics, basically, you remember Newton was very concerned with, well, not only Newton was basically combining that narrative for that came to him from many hundreds of years before. But he was very concerned with how do things move when no forces are acting, when no interactions happen, how would they remain in motion, and so on. So this notion of geodesic and straight line is basically encoding that free motion, that uninteracting motion that what we call a uniform motion in physics. And so the notion of force is a direct alteration of that. So this equation here, when you write it down in a local chart, is actually a differential equation. It's a second order differential equation. Notice there's a derivative here with respect to time, and then there's the covariant derivative that contains the ordinary derivative there. So you will get a degree 2, order 2 ordinary differential equation. And if you plug in the Levi-Civita connection of an Euclidean metric, you will recover acceleration equals 0. So you will recover literal straight lines in the physical sense. Okay, so Newtonian mechanics then, and that's really the end for me today, is simply assuming there is a notion of potential, so a notion of how things are gonna, so potential is a word that is referring to that something could be something, it has the potential to do something. So it's a function defined on our space. And remember that the presence of a metric allows us to define a gradient. So we've seen that this thing, it's a one form, right? But remember that the presence of a metric gave us the musical isomorphism. So that meant that I could send one forms to vector fields. So I can define the gradient. I could say gradient, the metric gradient, as, well, I have sharp as the inverse of flat, and flat, so sharp is the inverse of flat, and flat is the natural map that sends vector fields to one forms in the following natural way. So obviously it sends a vector field to G, fill the first argument, give the other entry. And so the metric gradient is basically, we will denote it like this, is defined as sharp of D. So D functions to one forms, sharp one forms to the vector field. And so now I can say this is my force field that's going to alter how straight lines work. And so Newton's equation F equals ma in this context becomes, well, how a curve parallel transports itself modified by the presence of a potential with a minus sign, some conventions. Well, and this notation is kind of confusing, so it's just So I'm going to leave it there, and tomorrow we'll explain a little bit the canonical formalism, and I'll give you some pointers on how to deal with physical dimension and dimensional analysis in linear mathematics. Bye.